All right, we're on part C, problem 10 of the final exam practice, and we want to decide if this series starting at n equals 2 going to infinity of negative 1 to the power n over n log n is absolutely convergent, conditionally convergent, or divergent. Okay, so first we want to test for absolute convergence. We notice that this series is alternating because we see this negative 1 to the power n feature. Okay. So what we want to do is take a look at the absolute value of each of the terms. And so this is going to be equal to 1 over n log n, and because, of course, n is greater than 2, first of all, so it's positive. Log n is positive when the input is greater than 1. So this is a positive number, and then the only thing that's negative here in this expression is the negative 1 to the power n, potentially. So either way, the absolute value is always equal to 1 there, so we just replace it with a 1. And so this is the function that we're considering now, and we want to know if the series 1 over n log n goes from 2 to infinity, is convergent or divergent, right? So this is the series of absolute values. So to test absolute convergence, we want to test convergence of this series. And so to test convergence of this series, we're going to use the integral test. And so we need to show some things about this function. F of x equals x log x, 1 over x log x, right? Because this is the function that we're dealing with. So I can rewrite this function as x log x to the minus 1. Okay, so the reciprocal of x log x. And I just need to look at this function for values of x that are greater than 2. Because our n starts at 2, and so these are the only values of x that we're interested in. And we need to know a few things about this function. We need to know that this function is decreasing. We need to know that it's positive, which it certainly is. That's not an issue. And we need to know that it's continuous, which it is. Again, that's not an issue. So we just need to test whether or not it's decreasing. So to test whether or not it's decreasing, we just look at the derivative, and we want to show that the derivative is negative. So to show that the derivative is negative, I take the derivative. I'm going to use the chain rule because I have a function of x composed with another function, so the power function to the negative 1. And so I'm going to get a minus that comes down, right? Power is going to come down. I'll get x log x, stays inside. Power goes down to minus 2. And then I need to take the derivative of the inside and multiply by that. So derivative of x is just 1, so I retain log x. And then I get x times the derivative of log x, right, which is just equal to 1 over x times natural log of 10, because log of x is just log base 10 of x. So we know when this is natural log of e, so this is, natural log of x, which is log base e of x, then this formula just turns out as 1 over x times natural log of e, but natural log of e is equal to 1, and so we get the 1 over x that we expect to get for the natural log. So either way, we have x divided by x, so those are just going to cancel, so we don't really need to write those. And then we have 1 over natural log of x is just some positive number. Natural log of x is positive when x is greater than or equal to 2. So this whole term is positive, and we have this minus sign. This whole term is positive because everything is being squared. So this is a negative number for all values of x greater than or equal to 2. All right, so it is decreasing. Cool. So we checked all 3 conditions, all 3 hypotheses of the integral test. And so now what we want to do is integrate this function from 2 to positive infinity. And see if it's convergent or divergent, because this is a type 1 improper integral, right, because we're integrating over an infinite interval. So we can use substitution in this case. So we're just going to go ahead and make u equal to log of x. Then the derivative, so the reason that we're doing this is because then the derivative is of course 1 over x natural log of 10 and dx because we're writing the differential du. And of course we have 1 over x dx, 1 over x dx. So we'll just multiply by natural log of 10 here to get natural log of 10 du is equal to dx over x, which is of course this portion of our integrand, and then u equals log x is the other portion of our integrand. So either way, doing this substitution, well, so first of all, we get log of 2 as our lower bound of integration, because when x is equal to 2, u is equal to log of 2. But then to see what value u goes to as x goes to positive infinity, that's going to be our upper bound. So as x goes to positive infinity, log of x goes to positive infinity as well. And this is u, right? So u is going to positive infinity as x goes to positive infinity. And so we're going to replace this positive infinity, again, with another positive infinity. So not really a huge change there, but either way, this is now in terms of u, whereas that was in terms of x. Okay, and so the rest of the stuff inside was just 1 over u du. Oh, and I lost my factor of natural log of 10, which I'll just write here, and then pull out to the front, because of course it's not going to affect convergence. It's just a finite number. So this is natural log of 10 times the integral of log 2 to plus infinity of du divided by u, which is of course just natural log. And so we're looking at natural log of 10 times integral is equal to natural log of absolute value of u. Of course, these are all positive values of u, but it's kind of redundant to write that, but it's okay. And then I evaluate at log of 2, and then take the limit as u goes to positive infinity. And of course this diverges, right? This goes to positive infinity. This diverges, right? And so we see that our series is not absolutely convergent because the series of absolute values diverges. So let's look at what we can say about conditional convergence now. And so we know it's an alternating series, and so we're going to try to use the alternating series test. So there are two conditions that we need to satisfy for the alternating series test. So that's these bn's, which are the absolute value of the an's, right? So we've already calculated this. It's 1 over n log n. We just want to make sure that these are decreasing. And of course they are, because this denominator is is less than if I were to write n plus 1 times log of n plus 1, because both n and log n are increasing functions, so the denominator got larger here, and this is our bn plus 1. And so of course we are decreasing, our sequence is decreasing, the absolute values. And we also want to show that the limit as n goes to infinity of 1 over n log n is equal to 0, right? These are the two conditions that our terms need to satisfy to prove convergence of our alternating series. And so, I mean, of course this is true, and the reason that it's true is because 1 over n log n is always positive for values of n greater than or equal to 2, and it's in fact less than, let's say for values of n greater than or equal to 3, this is going to be less than 1 over n, and we know that the limit of 0 as n goes to infinity is of course 0, the limit of 1 over n as n goes to infinity is also 0, and then we see by the squeeze theorem that we get 0 for this limit. So this is in fact true, it's decreasing, so terms go to 0 and they decrease. So by the alternating series theorem, or the alternating series test, we're going to have convergence of our series. So then we see that our series n equals 2 to infinity, minus 1 to the n over n log n converges, but the absolute values diverge, so this is conditionally convergent. All right, so that's all we can say about this series. All right, on to the next one.